Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, as you know that from time to time we try to bring for you different subjects, and under these subjects we try to bring for you different topics. Number of times we start with a new series, and today also we are going to start with a very new series in the subject area called chemistry. Dear friends, from today onwards we are going to talk on organic reactions. This is the first lecture in the series. So today we would be discussing about the organic reactions and would be knowing different organic reactions, and for this we have again with us in our studios Dr. K.K. Arora. Dr. Arora is Associate Professor in Department of Chemistry, Zakir Hussain, Delhi College, University of Delhi. So dear friends, let's try to understand what organic reactions are with the knowledge of Dr. K.K. Arora. Hello sir, welcome to the EDICET lecture, as we are starting with a new series on organic reactions, and this is the first lecture in the series. I would say that this would be the introductory or the basic lecture on the series.
Right. We will start one type of reaction.
Definitely.
Hello viewers, welcome to this new series of reactions. Here we will take up basically the type of organic reactions which we come across in the study of organic chemistry. We will discuss that how these reactions are named, or how different reactions are classified, what are their mechanisms. So, we will take one by one. Let us start with substitution reactions today. We will discuss two different mechanisms, that is SN1 and SN2, that we come across mainly, and other aspects of substitution reactions, particularly nucleophilic substitution reactions. That will be the topic for today's talk. Now, here this is a reaction. Some molecule has reacted with sodium hydroxide, some new molecule has been formed. Since this is an organic molecule, we will call this reaction as an organic reaction. But how this reaction has happened? We find that what change has occurred in this reaction: one carbon-bromine bond has been cleaved and one carbon-oxygen bond has been formed. The OH that was here with sodium is now a part of this molecule. A bromine that was a part of this organic molecule is now with sodium. So, what we find that this bromine basically has been replaced by hydroxyl group. So, one bond between carbon and bromine has been cleaved, one bond between carbon and oxygen is being formed. So, basically what we can say that organic reactions involve bond making and bond breaking, although even inorganic reactions will also involve the same thing, but since we are specifying the organic reactions, that is why I am using the term organic here. So, in general we can write a reaction that there are certain reactants, there is a molecule that may call reagent, then there are certain reaction conditions, they are specified. Reaction conditions may involve temperature, pressure, solvent, etc. And then certain products are formed. This is a way we generally write a chemical reaction. In a chemical reaction, which bonds are broken, which bonds are formed, and in what order? That is, first bond is cleaved or first a bond is formed, or which bond is cleaved or which bond is formed, what is their sequence, what is their order. This is known as the mechanism of the reaction. So, generally students are very much afraid about the mechanisms of the reactions. So, mechanisms are not very difficult thing, not very special. Mechanism just involves the sequence of cleavage or formation of bonds. We start from a particular reactant and we end up with a particular product. So, logical reasoning helps in understanding organic reactions. So, if we go through a chemical reaction logically, where from this logic comes? Basically, a logic in our organic reaction comes that where the electrons are moving, where there is an electron deficient center, where there is an electron excess center, and that decides that how the bond will be cleaved and how the bond will be formed. So, looking at the structure of basic organic molecule, which we generally call as substrate, the reactions can be classified into these 4 main groups. One are substitution reactions. In this substitution reaction, one atom or group from the substrate molecule is replaced by another group or atom. Then addition reactions. In addition reactions, some molecule comes and it adds on to the substrate molecules. So, for addition, our substrate molecule must have some pi bonds, where the reagent molecule, it comes and forms the bond with it. So, we call this as the addition reaction. Then elimination reactions. In elimination reaction, some part of the reagent helps in such a way so that our substrate molecule loses certain things. The group which is lost may be lost as a smaller molecule generally, and unsaturated molecules are generally obtained, or cyclic compounds are obtained by elimination reactions. And then there are 4th type of reactions which are called rearrangement reactions. In this rearrangement reaction, nothing comes in, nothing goes out, but what happens, the basic structure of the molecule, it changes. Some rearrangement occurs, obviously for that some bonds are cleaved, some new bonds are formed, but the molecular formula of the molecule, starting molecule, that remains same. Such reactions are classified as rearrangement reactions. Now, whenever these reactions they proceed or they occur, there are certain other molecules which also take part in them, and we call those as reagents. Reagents may be the molecule as such which we are using, or an intermediate which is obtained. Generally, these intermediates are also called as reactive intermediates because they react very quickly with the substrate molecules. But we classify these reagents generally into 3 main classes: nucleophiles, electrophiles, and free radicals. Nucleophiles are such species which are positive charge center loving, means they have excess of electrons with them. They might be having a lone pair of electrons, or it might be a pair of electrons with a negative charge. Electrophiles are those species which are seeking electrons. They are electron deficient species. They may be Lewis acids like aluminum chloride, etc., or they may be positive charge centers, that is, they have a positive charge on them like carbocations, etc. So, such species are called electrophiles. And then free radicals. Free radicals are sometimes also referred in the books these days only as radicals. These are the species which have one unpaired electron. So, they also have a tendency to accept or share this single electron so as to form a bond. Then there may be other type of reactive intermediates or reagents which are not very common. Here I have taken 4 common types of reactions and 3 common reagents. Now, each of these reactions can occur with the help of any of these reagent. So, suppose a substitution reaction, it can occur with the help of nucleophiles, then we will call it as a nucleophilic substitution reaction. It may occur with the help of electrophiles, we will call it as electrophilic substitution reaction, or if it proceeds with the help of free radicals, then we will call it as a free radical substitution reaction. Similarly, the addition reactions or elimination reactions, etc., they are also named. So, amongst these reactions, today we will start with nucleophilic substitution reactions. Nucleophilic substitution reaction we generally encounter for the first time while studying organic chemistry in the topic of alkyl halides. They are the typical reactions for alkyl halides. This is any alkyl halide. This is a nucleophile. Nucleophile is reacting with this molecule and replacing this halogen, and this nucleophile part now is attached to this alkyl group, and we get a new molecule, and this halide ion has been replaced. So, this is a nucleophilic substitution reaction. There are 3 possible mechanisms which have been observed for this reaction in different types of substituents, that is different type of alkyl halides having different type of substituents, and they are named as SN2, SN1 and SNI. We will take up these mechanisms and understand what are the factors which play a role in a particular mechanism. Mechanism that is being followed by a reaction, it depends upon the nature of substrate and nature of reagent as well as reaction conditions. As I said that alkyl halides undergo this nucleophilic substitution reaction with 3 different mechanisms. So, which mechanism will be followed by a particular molecule will depend upon all these 3 factors. Here in this particular type of reactions which we are going to discuss, our reagent is a nucleophile, and specifically I am going to discuss these reactions today for alkyl halides only. So, our substrates are alkyl halides, but they again may have different nature, means there may be different alkyl groups or different aryl groups and then different halogens in the molecule. And then what are the reaction conditions, that is what is the solvent or at what temperature we are carrying out this reaction. This mechanism SN2, it has been named like this. It is nucleophilic substitution bimolecular or second order. This SN stands for substitution nucleophilic and this 2 stands for that this reaction is bimolecular or second order. The name second order comes after studying the kinetics of this reaction. Let us take an example. When the treatment of bromomethane is carried out with sodium hydroxide, we observe that methanol is formed and bromide ion is replaced. Experimental facts for this reaction, they show that when the concentration of the substrate, that is methyl bromide, is doubled, rate is doubled. It means the rate depends on the concentration of bromomethane with raised to the power 1. Then when the concentration of hydroxide ion is doubled, again it is found that rate doubles. It means rate of the reaction also depends on the concentration of hydroxide. Means in this particular example, experimental facts tell us that overall rate of the reaction depends upon both the substrate as well as nucleophile, and the order with respect to each of these substance is 1. So, we can write the rate equation as K concentration of bromomethane into concentration of hydroxide raised to the power 1 in each case. So, overall order of this reaction comes out to be 2. Right. So, this 2 here is representing, you can say, order of the reaction also, that this is a second order reaction. Based on this kinetics, and there are just 2 substances, both are involved in the rate determining step, a one step mechanism is proposed. It is said that this is an alkyl halide, a nucleophile attacks the carbon carrying halogen, then it passes through a transition state in which the bond between the carbon and the nucleophile is partly formed and the bond between the carbon and the leaving halogen is partly broken, and then this product is formed in which this halide ion has left. Now, in order to further classify this reaction species, we call nucleophile also as the attacking species or the attacking group, and the group which is leaving, like here it is halide ion, we also call it a leaving group, and this reaction passes through a transition state in which the carbon is partly attached to the leaving group and has partly formed the bond with the attacking group. Since this pair of electron, or we can say this negative charge, is now partly formed the bond with this carbon, so the negative charge on this oxygen is reduced, and these electrons have been taken up by the leaving halogen. So, this halide ion has acquired a partial negative charge. So, the total negative charge that was concentrated on the oxygen in the hydroxide ion is now distributed on the oxygen and the leaving halide ion in this transition state. And when a sigma bond is formed between this oxygen and carbon, halide ion leaves completely, the full negative charge is with this halogen. So, this is a one step process for this nucleophilic substitution reaction by SN2 mechanism. We call it as a bimolecular also, because there is a one step which is a rate determining step, and both the species, that is the reagent as well as substrate, are taking part in that. Two molecules are taking part in the rate determining step, and there is only single step involved. So, that is why it is also called a bimolecular reaction, means molecularity of this reaction is 2, overall order of this reaction is also 2. This is same thing is represented, that this hydroxide ion is attacking this carbon, and this is leaving, transition state is partially attached and this group is lost. Now, when we observe carefully, we find that the transition state here has 3 groups attached, which are 3 hydrogens shown here for simplicity. Now, they have come in one plane. Originally, this carbon is sp3 hybridized, and 3 hydrogens are present at the points which are the corners of a tetrahedron. Now, it has become planar. So, this transition state has got 5 groups attached to it. Although these 2 groups are not attached by full sigma bond, they are partially attached, but 5 groups are attached, and it has a tendency to lose one of the groups, so that it acquires again a tetrahedral structure. Now, when this leaves, halide ion leaves, then these 3 groups which had come in the plane, now they take a turn onto this side. We will talk about it while discussing the stereochemistry of this reaction. So, leaving group leaves from the direction opposite to the attacking nucleophile. If the leaving group is leaving from this side, because attacking group is attacking from this side, the leaving group cannot leave from that side. This is the energy progress for the reaction. As the reaction progresses, this is alkyl halide, this hydroxide ion, it is approaching, the energy starts increasing. It is transition state. When it has partially formed a bond, a partially bond is being cleaved. So, this is a high energy state, and then this leaves, this bond is formed and energy is again reduced, and we get the product. So, this shows the energy changes during the reaction. Now, this reaction will not be able to progress by this mechanism if during the reaction that much energy is not available, so that these reactants may reach to this transition state. They are getting this energy either by collision or the thermal energy, that is the temperature of the reaction, or by interaction with the solvent, whatsoever the factors could be. But this reaction will proceed only if so much energy is gained, so that they are able to reach this transition state. Then let us talk about the effect of different factors in this mechanism. Effect of nucleophile. Since this reaction proceeds by the attack of nucleophile on the substrate molecule, the reaction will proceed at a faster rate if the nucleophile is strong, because it will have a tendency to attack this carbon and form a bond easily, form a bond quickly. So, rate of the reaction will be fast. So, stronger nucleophile will help in the progress of this reaction at a faster rate. Now, what type of nucleophiles are stronger nucleophiles? A species with a negative charge is a stronger nucleophile. than the corresponding neutral species. I would like to add here, although you may be knowing this thing, that all nucleophiles are also bases, because they have a pair of electron which they can share. But the difference between the basic character or basicity and the nucleophilicity is that basicity is the interaction of the species with respect to H plus ions, and we talk about nucleophilicity with their interaction with respect to carbon. So, since we are studying this reaction on carbon containing halogens here, so we will talk about the nucleophilicity. So, a species with a negative charge is a stronger nucleophile than their corresponding neutral species. It means, for example, water. Water has oxygen, and oxygen has got 2 lone pairs of electron here. It loses one H plus and it becomes hydroxide ions. This negative charge is obviously on this oxygen. Now again this oxygen now has a lone pair of electrons with negative charge. So hydroxide ion has a higher tendency to share a pair of electron, so it is a stronger nucleophile than water. Similarly, amide ion. Amide ion is a stronger nucleophile than ammonia, although ammonia is also nucleophile because nitrogen has a lone pair of electrons by which it can attack. If we look at the atoms in the periodic table, we will find that nucleophilicity decreases from left to right in the periodic table. For example, hydroxide ion is stronger nucleophile than fluoride ion. Here attacking species is oxygen, here it is fluorine. Oxygen comes in the periodic table in the same period before fluorine. Fluorine is more electronegative than oxygen. So fluorine has higher tendency to keep the pair of electrons with it. So it is having lesser tendency to share it in comparison to hydroxide ion. So that is why hydroxide ion is a stronger nucleophile. Similarly, if we compare the neutral species, the species in ammonia is nitrogen with a pair of electron, and in water it is oxygen with a pair of electron. Nitrogen comes before oxygen in periodic table in the same period. Oxygen is more electronegative than nitrogen. So obviously oxygen has more tendency to keep the electrons with it, and nitrogen has higher tendency to share in comparison to that of water. So that is why ammonia is a stronger nucleophile than water. Then nucleophilicity decreases down the group in periodic table. As you move down in a periodic table, what you find that size of the atom increases, number of electrons in the valence shell, that remains same. So as the size increases, then their outermost electrons, they are although not very strongly held by the nucleophile, by the nucleus, and also the size of the atom is larger. This pair of electron can be shared from a longer distance. So that is why iodide ion is a better nucleophile than bromide, than chloride, and then fluoride. Electronegativity can also be considered for this. Fluorine is most electronegative, has the minimum tendency to share, whereas iodine has minimum electronegativity amongst these, so has maximum tendency to share the pair of electrons. So this way we can compare the nucleophilicity of different species, and what we conclude that if our nucleophile is a stronger nucleophile, then it will go and attack the alkyl halide molecule, that is a carbon carrying halogen, and reaction will be a faster reaction by SN2 mechanism. Then effect of leaving group. Leaving group means the halide ion here for specifically, although when we will discuss this reaction with respect to other functional groups, then in general we will talk about other factors for the leaving group. A good leaving group must be an electron withdrawing so as to polarize the carbon halogen bond. There is a carbon halogen bond in the molecule. If this halogen has got higher electronegativity, only then it will be partially polarized. So more is the electronegativity or more is the electron withdrawing power of this, more the bond will be polarized. But this is not the only factor, because had this been the only factor, then CF bond Fluorine should have been the better leaving group because it has maximum electronegativity, but CF bond is also very strong bonds and a short bond. So, more energy is required to break it. A stable entity with a pair of electrons means a group, that good leaving group is one which becomes stable after it accepts a pair of electron. The weak bases, which are the anions of strong acids, are also good leaving groups. A larger size leaving groups are also good leaving groups because they will reduce the steric hindrance in the transition state. Anions of strong bases means, like if I compare the halogen acids Hi, HBr, HCl and HF, the strongest acid is Hi. So, anion I minus is the weakest base amongst these. So, for halide ions, the sequence or the order as a leaving group is also like this as it was for attacking group. Iodide ion is a better nucleophile as well as a better leaving group also. That is why iodide ion is sometimes used as catalyst in certain nucleophilic substitution reactions also. Then we talk about the substrate molecule. This is the carbon on which the nucleophile has to attack. If it is a methyl group, means this carbon has all the three groups attached to it are hydrogen. In a primary alkyl halide, say in ethyl group, that is haloethane, this will be a methyl group. If it is an isopropyl group, then there are two methyl groups, and in a tertiary butyl group, there are three methyl groups. In all these cases, nucleophile has to attack the same carbon. So, larger are these groups, or more is the number of these bulkier groups, it will be more difficult for the nucleophile to approach and form a bond with this carbon, or in simple words we say attack this carbon. So, the rate of reaction decreases as this carbon is more and more highly substituted. Like in these four compounds, methyl halide, ethyl halide, isopropyl halide and tertiary halide, when this halogen is bromine, the ratio of reactivity is found to be like with methyl, if it is 150, with ethyl it is 1, with isopropyl it becomes 0.01, that is 1/100th of this, and with tertiary it becomes very slow, 0.0001 with respect to this primary alkyl halide. So, we say that a rate by SN2 mechanism decreases as we move from a primary to secondary to tertiary alkyl halide. Then this shows something else. This shows the transition state, that this Z is the attacking group has partly formed a bond, halide ion, this carbon halogen bond is partly broken, and in case of methyl, ethyl, isopropyl and tertiary butyl, what we find that as you move from here to this, our transition state is now more and more crowded, because in transition state I said there are 5 groups attached to it. Here there are 2 groups but 3 hydrogens. 1 methyl has come, 2 methyls have come, and in this case there are 3 methyl, 1 leaving group and 1 this attacking nucleophile. So, these are all 5 bigger groups. So, what happens? The transition state which is formed is also more and more less stable, that is it is more energetic, that is in order to reach this transition state more energy is required. So, obviously reaction rate becomes slow, or sometimes under certain conditions reaction may not proceed by this mechanism when we move from primary to tertiary alkyl halides. Then as I said, we will talk about the stereochemistry of SN2 reaction. Stereochemistry means what happens to the molecule if our molecule is optically active. Only then we can observe the stereo factors. This is R2-bromobutane. This R refers to the isomer which are named according to IUPAC system as R or S. This is the nucleophile attacking. As I discussed before, that nucleophile attacks from one side and this direction is opposite to the direction of the leaving group, then this leaving group leaves from the other side. So, these 3 groups which were on this side in a tetrahedral, in transition state they come in one plane and then the product they go in the other direction. So, what we find that if we just do not consider this group, the leaving group and this attacking group, we find that this part is now the mirror image of this part. We say that this reaction involves the inversion of configuration. Although same molecule is not obtained, a group has changed. As in case of R 2-bromobutane, we obtain S-butane 2-ol. So, what has happened? Configuration of the starting molecule, it gets inverted by this mechanism, and this inversion is also known as Walden inversion. It was studied by scientist Walden, so it is named after his name, Walden inversion. So, SN2 mechanism reaction proceeds with inversion of configuration. Then let us move on to the other mechanism, we call it as SN1 mechanism. The name for this, full name for this SN1 is nucleophilic substitution unimolecular or first order reaction. Let us take an example for this. This tertiary butyl bromide, when it is hydrolyzed with water or treated with water, this Br is again replaced by OH. So, it is a substitution reaction, water is acting as a nucleophile, so it is a nucleophilic substitution reaction. When kinetics of this reaction was studied, it was found that rate depends on the concentration of alkyl halide only. The rate is independent of the concentration of this water, that is a nucleophile that we have taken. So, the rate equation that we write is rate is proportional to concentration of this alkyl halide only. Since our nucleophile is definitely taking part in the reaction, but it is not coming in the rate equation, it means it is not involved in a slow step. So, it indicates that this reaction should involve more than one step. So, on this basis a two-step mechanism is proposed for this, that the first step is slow or rate determining, where only alkyl halide is involved. The second step is the fast step where our nucleophile is involved. So, the mechanism is written like this, that first step, it is cleavage of carbon halogen bond. This carbon halogen bond, when is cleaved, you will find that this halogen leaves with a negative charge. So, carbon is left with a positive charge, and such species they are known as carbocations. So, first step in the SN1 mechanism involves the formation of carbocation. Now, the question comes that if there is no role of any other nucleophile or anything, how this bond has been cleaved, because we keep alkyl halides in the bottles in the laboratory. We find them as a molecule of alkyl halide and not a carbocation and a halide ion, they are not ionic substances. So, how this bond is cleaved at the time of reaction? It is only with the help of polar solvents. Actually, this bond is partially polarized due to the electronegativity difference of halogen and carbon. The carbon has delta positive charge and this halogen has got delta negative charge. But when we put some polar solvent in this, then this gets surrounded by one type of the end of the solvent, this gets surrounded by the other charged end of the solvent molecules, and that interaction between the oppositely charged end of the solvent molecule and this carbon or halogen releases some energy, and that energy ultimately helps in cleavage of this bond and the carbocations are formed. The second step now involves the attack of the nucleophile, where the product is obtained. This positively charged carbon, that is a carbocation, combines with the nucleophile and we get the product. A bond is formed between this carbon and this nucleophile. The reaction coordinate can be shown like this, that alkyl halide and the nucleophile, they are interacting, but before nucleophile has played any role, this alkyl halide has cleaved to form a carbocation and halide ion, and now it is the role of nucleophile, it combines with this carbocation to give the product. So, this is intermediate which is formed. Now, in this reaction there are two different transition states. This is first transition state, this is the second transition state. Because there are two steps, every step has got its own transition state. This is a rate limiting transition state because the second step will occur only if the carbocation is formed. So, faster is the rate of the formation of carbocation, faster will be the overall reaction. If this step is slow, overall reaction will be slow. So, rate determining step is this step, formation of carbocation. Now, let us talk about the effect of other factors now, effect of nucleophiles. This is favored with a neutral or weak nucleophiles like water, alcohol, amines, etc. Because if our nucleophiles are stronger, then what will happen? They will go and attack the carbon, they will try to form a bond quickly. So, the mechanism will shift to SN2. So, SN1 mechanism will be favored if our nucleophile is a weak nucleophile, is just sitting aside and waiting for the formation of carbocation, and once the carbocation is formed, it goes and just forms a bond. Then effect of leaving group, it is same as that for an SN2 mechanism, because a leaving group obviously requires a cleavage of bond, and easier the bond that is cleaved, faster will be the reaction. So, these factors are similar for both the mechanisms SN1 and SN2. Later we shall discuss that how this leaving group plays a role when I will discuss the role of solvent also. Now, briefly I will take up what are carbocations which are formed as intermediate in these reactions. Carbocations are positively charged species where the positive charge is present on carbon. Here the carbon is sp2 hybridized. So, 3 groups on the carbon, they are present in one plane. This box shows the plane where the 3 substances are there, and this represents the empty p orbital. One lobe of the p orbital is above the plane and other lobe is below the plane. So, this is the basic structure of carbocation, which is formed as intermediate in SN1 mechanism. The carbocations at tertiary, when carbon has got 3 alkyl groups, when this positively charged carbon has got 2 alkyl groups, we call it as a secondary carbocation. When it has got a 1 alkyl group, we call it as a primary carbocation, and when all are hydrogen, it is simple methyl cation. These carbocations, this shows their order of stability. Now, why they are stable in this order? Because this positive charge is stabilized by the inductive effect of these methyl groups, which is electron releasing, and second by the hyperconjugation. So many hydrogens are there, they form hyperconjugative structures because this next carbon has got a positive charge. So, more are the hyperconjugative structures, more is the stability. So, we find that these tertiary carbocations are more stable than secondary and then primary and then simple methyl. And I said just before that more stable the carbocation, more easily it will be formed. So, that will tell us about the rate of reaction also. So, order of reactivity in SN1 mechanism depends on this. It is directly related to the stability of intermediate, that is carbocation. This is their order of stability for carbocations: tertiary, secondary, primary and then methyl, and same will be the order of reactivity for different alkyl halides. Tertiary alkyl halide will react at a faster rate by this mechanism than secondary, then primary and then simple methyl halide. This is an example: tertiary butyl bromide, this isopropyl bromide, this is ethyl bromide and this is methyl bromide. When they are subjected to substitution by water in formic acid, this bromine is replaced by OH. This is a general reaction for all these carbocations, and their relative rate comes out to be, if for methyl bromide we take the rate to be 1, then for ethyl it is 1.7, for isopropyl it is 45, and for tertiary butyl it is very large, 100 million. Means this tertiary halide reacts at a very fast rate under the similar condition where methyl halide reacts at a very slow rate. So, this order of reactivity is due to the same reason that this will form a tertiary butyl carbocation, which is very highly stable carbocation. Then effect of solvent. As I said before, that this bond, it gets polarized and ultimately is cleaved due to the polarity of the solvent. So, this reaction is favored by polar solvent. Here is again a comparison of rate in different solvents for a reaction of tertiary butyl chloride, where we studied this SN1 mechanism. A tertiary butyl chloride, when the solvent was water, methanol, ethanol, acetone and diethyl ether. As you move down this series, what we find that their polarity is decreasing. Water is most polar, then methanol can form the hydrogen bond also, then ethanol, then acetone, and then very less polar solvent diethyl ether. And again we find that if the rate with acetone is taken as 1, then with ethanol is 200 times, with methanol 1000 times, with water it is 8000 times. And in diethyl ether it is just 0.001 of the, that is 1000th of the rate in acetone. So, this clearly indicates that by changing the solvent, how the overall rate of the reaction will be affected. So, SN1 mechanism is favored by polar solvents. Then stereochemistry of this SN1 reaction. As I said before, that carbocations are planar. Now, once a planar species is there, and we had discussed that one lobe of the empty p orbital is on this side and another lobe is on this side of this plane. Now, nucleophile can attack from both the sides. This water molecule says nucleophile here, it can come from this side as well as it can come from this side and form the bond. If it comes from this side, then these three substituents will move on to this side and we will get a tetrahedral structure. And if it comes from this side, these three groups will move on to this side and that will form a opposite tetrahedral structure. So, if these three groups are different, here we have shown just methyl groups, if these three are different, then obviously we will get both the isomers of the product, means we will get a racemic mixture. So, product is a racemic mixture. I will discuss little more about it. Let us move on to next slide and see in detail. This is one alkyl halide. It is basically 2-bromobutane. When this bromine is lost in SN1 mechanism, we get this carbocation which is planar. Now, on this planar carbocation, this say hydroxide ion or water can attack from this side as well as from this side, that is shown here in this structure. This can attack from this side as well as can attack from this side. When it attacks from this side, these three substituents move on to one direction. If it attacks from this side, these three groups move on to another direction. So, we get both the isomers of 2-butanol. So, what we say, we are getting, since both the optical isomers, so it is a racemic mixture. Half the molecules are dextrorotatory, half the molecules are levorotatory. But actually in experiments it has been observed that by SN1 reaction, again inversion is slightly more than the retention, means the product that we get is not 100% racemic mixture, it has got slightly higher concentration of the inverted product. And that can be explained on this basis that as this halide ion has left and it has formed a planar structure, this halide ion, once it is formed, now this is carbocation and that halide ion is negatively charged bromide ion, that will be on the same site from where it was leaving. So, now the attacking group in the meantime has more chances of attacking from this side. So, what will happen? A random discussion when we will do, till the time this halide ion moves slightly away from here, so that the nucleophile can attack from this side also, there is a possibility that more nucleophiles attack from this side, which is leading to inversion. So, we find that final product, although it is racemic but not 100% racemic mixture, slightly inverted product is more. in comparison to the product in which configuration has been retained. Then one more thing that we observed in SN1 reactions are the rearrangement. Sometimes the products are obtained in which the rearrangement of the carbon skeleton has occurred, like in this molecule 2-chloro-3-methyl butane. This is the starting compound. When it is hydrolyzed with water, that is Cl is to be substituted by water, this is our expected product, that Cl will move and OH will come here. So, we expect this 3-methyl butane 2-ol, but along with this we get 2-methyl butane 2-ol. Now, this is a rearranged product. Rearranged means somehow this chlorine is lost from here and the hydroxide has occupied this position. So, some movement has occurred and this is hydrogen that has changed its place from here to this carbon. And in this reaction this 2-methyl butane 2-ol is obtained in larger amounts rather. So, in comparison to the expected product, the unexpected product is obtained in larger amount. So, we explain the formation of these products in this way, that the reaction is proceeding by SN1 mechanism. The first step involves the cleavage of this carbon chlorine bond. The Cl is lost as Cl minus and we get this carbocation. Now, this is a secondary carbocation. This carbon with positive charge has got 2 carbons attached to it. It is a secondary carbocation. If a hydride ion shifts from here to this carbon, then positive charge will come to this carbon and we will get a tertiary carbocation. And tertiary carbocations are more stable than secondary. And whenever any such situation is there, then such a rearrangement occur by the shift of hydride ion or by the shift of some alkyl group in the carbocations, and the less stable carbocations get converted into more stable carbocation. So, we get this tertiary carbocation and now this captures the OH from water at this point and we get 2-methyl butane 2-ol, that is the B here, and when water comes here we get the product A here. Then about this rearrangement we can observe one more thing, that our nucleophile is stronger, then it will just go and attack and replace the leaving group and there will be no chances of rearrangement. If our nucleophile is weaker, first a carbocation has been formed, only then there will be some chance that it can be rearranged to more stable carbocation and then nucleophile comes to it. So, this particular reaction even confirms the mechanism also. This is a neopentyl bromide, although it is a primary alkyl halide. When it is treated with ethoxide ion is a strong nucleophile, it goes and attacks this carbon, this halide ion is replaced and we get this ether, that wherever the bromine was there, now we have this ethyl group, this ethoxide group. So, there is no rearrangement has occurred and we have obtained this ether. When our nucleophile was weak, that is we are doing the reaction with ethanol. Now, what happens? SN1 mechanism operates. First this halide ion leaves, we get a positive charge on this carbon, this is a primary carbocation, but by shifting this methyl group to this carbon we get a tertiary carbocation and such a rearrangement occurs and this tertiary carbocation now when the positive charge is on this carbon captures this ethoxide from the ethanol and we get this group, that is tertiary pentyl ethyl ether, and this is a rearranged product. Along with this we get some unsaturated product and alkene also. We will discuss about this later while discussing the elimination reactions. So, here at least we confirm one thing, that if the nucleophile is stronger, it goes and replaces the halide ion, no chances of rearrangement in SN2 mechanism, and in SN1 mechanism it leaves, carbocation is formed, there are chances that they can be rearranged to a more stable product and we get a rearranged product in this. Then there are some other type of halogen derivatives which are specially classified as benzyl and allyl. When these in benzyl and allyl halides, reaction proceed by SN2 mechanism, it proceeds as in other primary alkyl halide. This is a benzyl halide, when benzene ring CH2 and then halogen is there. and this is an allyl halide where carbon carrying halogen and next carbon to, that is carbon number 2 and 3, they have a double bond. They are called allylic halides, these are benzylic halides. When they are treated with nucleophiles, strong nucleophiles like hydroxide ion or ethoxide ion, etc., the reaction proceeds as usual as in other primary alkyl halides. But these halides, benzylic and allylic, they proceed the nucleophilic reaction by SN1 mechanism also. In SN1 mechanism, this halide ion leaves if our nucleophile is weak, and we get positive charge on this carbon, which is a benzyl carbocation, which is resonance stabilized. This positive charge is resonance stabilized with the benzene ring. It is more stable carbocation, formed very easily, and now like in weaker nucleophile like methanol combines with it and we get this ether. Similarly, in this allyl derivative, this is crotyl bromide, when this bromine leaves as bromide ion, positive charge comes here, this is in now allylic position to it, and this is stabilized by resonance. The positive charge here, this pair of electron comes here, we get another resonating structures. The positive charge is now on this carbon. Now, any of these structures can capture the water and we can get two different alcohols in this case, and reaction becomes very fast because in both the cases the carbocations are resonance stabilized. They are highly stable carbocations and reaction proceeds at a very faster rate even with weaker nucleophiles in case of aryl halides and allyl halides. Then in case of vinyl halides and aryl halides, they do not undergo SN2 reaction because the approach of the nucleophile is hindered due to electron repulsion. Aryl halides means the halogen is attached directly to benzene ring, and vinyl halides means when the halogen is attached to carbon which is attached to another carbon by double bond. So, carbon carrying halogen in both these cases, they have a next bond which is a pi bond in them, and if nucleophile tries to attack from the back side, there is a pi electron cloud which repels it. So, SN2 mechanism is not favored. They do not undergo even SN1 reaction because vinyl and allyl carbocations are very less stable, because in this case the halogen is attached to an sp2 hybridized carbon, and sp2 hybridized carbon forms a stronger bond, and it is not easy to break such a strong bond just by the energy received by solvation in polar solvents. So, vinyl halides and aryl halides are very less reactive or may not react at all by any of the two mechanisms, whereas benzyl halides and allyl halides are more reactive by both the mechanisms. Now, let us compare the two mechanisms SN1 and SN2. SN1 is unimolecular and it is a two-step mechanism. SN2 is bimolecular and it is a one-step mechanism. Rate of reaction. In SN1, it depends only on the substrate because that is involved only in the rate determining step. Substrate means here our alkyl halide about which we are talking, and then in SN2 mechanism it depends upon the concentration of both nucleophile as well as substrate. The nature of the nucleophile. SN1 mechanism is favored by neutral or weak nucleophiles, whereas SN2 is favored by strong nucleophiles. Role of solvent. SN1 mechanism is favored by polar protic solvents, where SN2 is favored by polar aprotic solvents. Alkyl groups. SN1 mechanism is favored by bulky alkyl groups, whereas SN2 mechanism is favored by less substituted alkyl groups. And stereochemistry. SN1 reaction generally proceeds with racemization, that is we obtain a racemic mixture, and in SN2 mechanism it is the inversion of configuration that occurs. Now, with respect to alkyl halide, if we compare that, if we move from methyl halide to primary to secondary to tertiary alkyl halide, rate increases by SN1 mechanism, rate decreases by SN2 mechanism. So, under a given set of condition, if we have a secondary alkyl halide, it may be proceeding to the formation of product partly by this mechanism, partly by another mechanism. or we can shift the reaction to a particular mechanism by adjusting the conditions, that is by adjusting the solvent or a particular nucleophile also. So, if it is methyl halide, if it proceeds under a set of condition by SN2 mechanism, tertiary halide proceeds by SN1 mechanism, we may get a mixed mechanism when it is a secondary alkyl halide. So, this was about two different mechanisms which we observe generally in alkyl halides. In my next lecture, we will talk about that how these reactions, nucleophilic substitution reactions, they are applied to other functional groups also. And we will also talk about a third mechanism, SN1 mechanism. So, we will discuss that formation of alkyl chlorides from alcohols by HCl. Although hydroxide is a stronger nucleophile than chloride, then how alkyl chlorides can be obtained from alcohols? Or conversion of alcohols into alkyl halides using PCl3, PBr3, PCl5, etc., where there are no halide ions in these. So, both these type of reactions actually involve SN1 mechanism. Then cleavage of ethers using HI also involves a nucleophilic substitution, hydrolysis of acid derivatives and interconversion of some acid derivatives. So, we will take up in our next lecture the SN1 mechanism of the nucleophilic substitution and then other type of functional groups where these reactions are used up. So, that is all for the day. Thank you.
With this note, thank you sir, thank you so very much. As we had already said that it is a series based lecture, we would be discussing more, as Dr. Arora said, that is there is lots to discuss and in future session we would be discussing more. With this note, thank you sir, thank you so very much for giving your precious time. Dear friends, if you want to access this particular lecture, you can access it with the help of YouTube. As we daily say that we upload our lectures on YouTube so that it becomes easier for you to view a particular lecture number of times, ample of times. And if you have any question regarding this particular lecture, you can mail us at info.cec@nic.in. Thank you sir, thank you once again.